Hello, this is the presentation for our work, Perturbation-based QE, which is an explainable, unsupervised word-level quality estimation method for Blackbox machine translation. This work is done at the Artificial Intelligence for Language Technologies, AI for LT, at the Karlsruhe Institute of Technology, Germany. First, I would like to explain the task of quality estimation. So the common machine translation evaluation setup is that we have some input source sentences. We feed it to some machine translation system that we want to evaluate. We get the output. We compare it to some gold standard reference translation in order to calculate some score, such as the blue score. However, the reference translations are not always easily available. Therefore, there has been research into quality estimation where the goal is to evaluate the machine translation output without the need for reference translation. In this work, we focus on word-level quality estimation with the goal of predict whether an output translation token is correct or not. The state-of-the-art approach to quality estimations are supervised. So they require gold standard quality assessment on the machine translation output. As you can see in the example here, the label would need to be on every single token in the translation on whether they are okay or bad. A drawback of this approach is that labeled data are very costly. And the other thing is that these supervised quality estimation models would only know about the errors that are presented in the training data. So they would only know about the errors that some specific machine translation system make on some data in some specific domain. So they are domain dependent and MT system dependent. Therefore, people have been looking into unsupervised quality estimation, where labeled quality estimation data are no longer required. In previous work, one way of doing it is to use glass box features of the machine translation system itself. So for example, people can use token output log probability, and then the one with low confidence would more likely to be a bad translation. The problem with this is that they require glass box access to the machine translation system, which is not always available. And as you can see in some modern day large language model, they only provide the API rather than the internal access of the model itself. The other way to do unsupervised quality estimation is to use parallel machine translation data to create some synthetic quality estimation data for training. So one way of doing it is to align some candidate machine translation output with some gold standard reference translation to find errors, or to use some language masking model on the reference data to generate errors. So in this approach, they would require pre-selected parallel machine translation data and also pre-selected candidate machine translation system. So this approach would have the same problem as for supervised quality estimation, because they would also be domain dependent and also MT system dependent. Therefore, in this work, we propose perturbation-based QE. We attempt to have a quality estimation approach that does not rely on labeled quality estimation data, nor machine translation parallel data, nor glass box access to the machine translation system. The motivation of our approach is a known issue of the recent day machine translation system, which is spurious correlation. So when the machine translation system is uncertain on some output, they would rely on some spurious correlation learned from the training data in order to make a decision. Our assumption here is that if an output word is influenced by too many source words in the source sentence, then it is likely to be unreliable. Here we have an example of translating English to German. So my friend has a PhD degree and now she is a professor. As you can see, when outputting the word Freunden, ideally a machine translation system should only look at two words in the source sentence, which is friend and she. Here, friend indicates the meaning of Freunden and she indicates the female form for Freundin in German. So our general idea is to perturb words in the source sentence one by one in order to find out which source words influence a single output word. And now we will go into more details of perturbation-based QE. The first step in our approach is perturbation generation, where we mask a single source word and then use a masked language model such as BERT to generate multiple different replacements. As you can see in the example here, we first mask the word John and then use some language masking model to generate different replacements such as he, Sam, James, or David. The next step is to translate all of those perturbed source sentences, as you can see here. And then we align the perturbed translation with the original translation. So as you can see in the result here, the column titles would be the original translation, the rows would be the different perturbed translation, and they are aligned at the word level. Here we try to categorize the different tokens in the original translation into one of the three categories. The first one is direct perturbation outcome. So this is the column. This is the translation that is directly translated from the perturbed source word. So it is likely to have a different version across all the perturbed translation. So recall that we replaced the source word John with he, Sam, James, and David. So in this column, it would have different versions corresponding to the perturbation in every row. The second category is a translation that remains the same across all perturbation. And here we call it a consistent translation, where an example is the word Frau here. The last remaining category is inconsistent translation, where they have a few different versions of it across the different perturbation. An example of inconsistent translation is the word Quelle, where it has only two versions of it across all perturbation, which is Quelle and Fruja. So when a translation is inconsistent due to perturbing a source word, we say that that translation is influenced by the source word. So here we have the word Quelle is influenced by John. We do the same for the other words in the source sentence. So we perturb met, and then we realize that in, der, and Quelle is influenced by met. We perturb the words his and realize that no word in the translation is influenced by his. We perturbed the word wife and then realize that no word in the translation is influenced by wife, and so on. In the end, we gather the statistic and we find out that John is influenced by 0 source word, Quelle is influenced by 4 source words, and then we compare it to some hyperparameter threshold. And if the number of influenced source word is larger than the certain threshold, then we mark the word as bad. So here, Quelle is marked as bad. That is the overall description of our method. And now we will come to the experiments. Our first experiment is an overall evaluation to compare with the other quality estimation methods. So we base this experiment on the WMT21 shared task, where the data is the input source sentence, the translation, and the word level okay or bad label on the translation. The language pairs that we experiment with is English to German and English to Chinese, which is supervised in the shared task, and also English to Japanese and English to Czech, which is the zero-shot direction in the shared task. However, our approach is unsupervised, so we only use the development split of English to German and English to Chinese in order to do hyperparameter tuning. The evaluated machine translation systems are the FAIRSEC traditional encoder-decoder MT. The evaluation metric is the Matthew Correlation Coefficient, MCC score, where the closer to 1, the better the prediction, and 0 score would mean random prediction. We selected 2 QE baseline in order to compare our approach with. The first one is the unsupervised method that uses the output log probability to perform prediction. So if the log probability is less than a certain threshold, then we mark the output token as a bad translation. The second approach is supervised, where we use the WMT21 share task supervised baseline. So this is the result of our first experiment. As you can see, our approach, perturbation-based QE, outperformed the naive log probability baseline in all directions. However, when we compare our approach with the supervised baseline, then we see that our approach has worse performance than the supervised baseline on English to German and English to Chinese. So we can conclude that when labeled data is available, then using the supervised approaches would be more beneficial than using our approaches. However, when we look at English to Japanese and English to Czech, which is the zero-shot or untuned direction, we see that our approach have either better or similar performance to the supervised baseline. And recall that in the supervised baseline, they trained in a zero-shot manner, which is rely on the labeled data of many different other language pairs. Whereas in our approach, we do not rely on labeled data. Therefore, we can conclude that our approach is more data efficient than the supervised baseline when there is no direct labeled data available of the language of interest. Another observation is that for the supervised baseline, the zero-shot English to Japanese has a lot worse performance than the other language direction. We hypothesize that this is possibly due to the low language similarity between English to Japanese to the other language pairs in the training data. So they would further indicate the data-dependent issues of the supervised quality estimation approaches. Now we will come to our second experiment. As you have seen before, the common evaluation setting for quality estimation approaches is in domain. So the quality estimation test data has the same domain as the quality estimation training data, and that the machine translation system used to generate the quality estimation training data is the same as the one used to create the test data. So this would not be generalizable when accessing a new machine translation system on a new dataset. Therefore, we perform experiment on out-of-domain and unseen empty system. So for unseen empty system, we test quality estimation approaches on the prompt-based decoder-only large language model, as opposed to the traditional encoder-decoder machine translation system as we have seen in the in-domain setting. And for out-of-domain data, we try to see whether the quality estimation approaches can detect different types of translation error. The first type of error that we want to evaluate on is gender bias. The data set we use in these experiments is we know MT, where they include input short sentences with marked gender roles. So for example, the doctor asked the nurse to help her in the operation. The doctor here is the word of interest. We know MT includes an evaluation protocol in order to identify whether the MT system output the correct gender form. And then we perform quality estimation by running this QE method on the MT system output on we know MT data. And then we assess how much of the wrong gender tokens marked by we know MT are successfully predicted as bad by the QE methods. And the matrix we use here is the recall. Similarly, we try to see if the quality estimation methods can detect word sense disambiguation error. And the data set here is MooCal, where it includes short sentences with ambiguous words. And it also includes an evaluation protocol to identify whether the MT system output the correct sense of the ambiguous word. Similarly here, we run the quality estimation methods on the MT system output on MooCal data, and then we assess how much of the wrong sense tokens marked by MooCal are successfully predicted as bad by the QE method. And the matrix we use here is also the recall. This is the result of the experiment. Here you can see the top part of the table is the result on detecting gender bias. The bottom part is on detecting word sense disambiguation. The left part is detecting errors made by the traditional encoder-decoder machine translation. And the right part is on detecting the errors made by the non-traditional prompt-based large language model. As we can see, in all different cases, our perturbation-based QE approach outperforms all the other baselines. Another observation is that for detecting gender bias, the supervised quality estimation approach can almost detect no gender bias at all, and their performance is even worse than the naive log probability baseline. So this strengthens our hypothesis is that supervised quality estimation methods are very domain dependent, because most likely it haven't seen many gender errors in the training data. We also see that there is a larger performance gap between our approach and the supervised approach in the prompt-based large language model compared to the traditional encoder-decoder MT. So the performance gap here and here is larger than in the traditional in-domain setting. This is also an indication that the supervised quality estimation model are more MT system dependent. It would perform better on the translation output of an MT model that it has known during training rather than a brand new machine translation system. Our next experiment is on robustness with respect to hyperparameter choices. Previously, we tuned our hyperparameters for English to German and English to Chinese using their labeled development set. And then we applied the best hyperparameter setting of English to German on English to Czech, and we applied the best hyperparameter setting of English to Chinese on English to Japanese because we expect more language similarity in this setting. So we refer to these as ideal hyperparameter setting. And in this experiment, we try a suboptimal hyperparameter setting where we apply the best hyperparameters of English to German on English to Chinese and English to Japanese. And we apply the best hyperparameter found of English to Chinese on English to German and English to Czech. We also perform ablation experiments where we try different choices for the discrete hyperparameters to see how it affects the performance of our approach. So this is the result. As you can see in this table, comparing ideal to suboptimal hyperparameters, the MCC score in general deviates by only around 0.001 score, which is not significant. And also in the second table where we use different setting for our approach. So for example, perturbing different set of words in the source sentence using different language masking model in order to perform perturbation or using different alignment method, we see that the MCC score also in general doesn't change that much. So we can conclude that our approach is robust to hyperparameters and it is not too dependent on labeled development data for hyperparameter tuning. Next, we show an example of the explainability power of our approach on We Know MT. Here we have an example. The chef gave the housekeeper a tip because he was helpful, and then the translation made by the machine translation system. Here we can see that the MT system output the female version for housekeeper, which is wrong, indicated by the word he in the source sentence. So ideally, the MT system should only look at the word he in the source sentence to decide the gender for the word housekeeper. However, our approach shows that when we perturb chef, gave, tip, was helpful in the source sentence, then the translation of housekeepers changes between male and female. It doesn't change when we perturb the word he, which means that the MT system is focused on the wrong part of the sentence in order to output the gender form of housekeeper. So to conclude, in this work, we propose perturbation-based QE, which is a quality estimation approach that is model agnostic, and it works for any black box system such as the API-only large language model. It does not rely on labeled data, which makes it more generalizable, more domain independent, and MT system independent. It is explainable, and it performs better than supervised method on zero-shot settings and better detects different types of errors. For future work, this idea can be applied to other text-based tasks like summarization or question answering in the same manner where we can minimally perturb the input and then analyze the output. Thank you for your attention.